Hello, everyone. So, last time you learned about atoms and elements and how they're different from molecules and compounds. You also learned about the atomic number, the chemical symbol, or the elemental symbol, as well as the atomic mass. You also learned about the concept of moles, right? The mole concept and the molar mass, and how that's basically similar to a formula mass, right? They're numerically equivalent, but the difference is the unit. So in formula mass, you have the atomic mass unit, AMU, whereas for molar mass, it's in grams per mole. And finally, you learned how to convert from mass in grams to number of moles to number of atoms. And so whenever you're converting from mass to number of moles, you need the molar mass. Whereas if you're converting from number of moles to number of atoms, you would need Avogadro's number, which is equivalent to this huge number, 6.02 times 10 to the 23rd power. And so in this chapter, we're going to extend that to molecules and compounds. And so mathematically speaking, we're going to try to convert the number of molecules, let's say number of molecules, to the mass of molecules and vice versa. And you're also going to learn how to name compounds, the nomenclature, right? So you should, let's say if I give you the chemical formula, how would you name that chemical? Or if I gave you the chemical name, how would you come up with its chemical formula? And finally, you're also you're going to learn the concept of mass percent or percent composition, mole ratio, and also empirical formula versus molecular formula, and then a little bit of organic chemistry, like naming the most basic organic molecules. So in the previous chapter, you learned about pure substance and how they're different from mixtures. A pure substance is basically something that contains a single component, whereas a mixture is composed of multiple different components mixed in together. You learned that there are two types of pure substances. There's elements and compounds, and these two are of course different, but they are related. Elements are basically the simplest building blocks of matter, right? They're composed of elements. You have sodium, for example, you have chlorine gas, you have gold, silver, so on and so forth. Basically, all the elements in the periodic table, those are elements. Elements that we know exist. And you can also consider homonuclear diatomic gases as pure elements. And these homonuclear diatomic gases are composed of elements with multiple atoms of the same element. Right, so diatomic meaning two atoms. So you have hydrogen gas, which has the chemical formula H2. You have oxygen gas, O2, nitrogen gas, fluorine gas, chlorine gas, so on and so forth. Compounds, on the other hand, are composed of multiple different elements. So, for example, you have table salt, which is sodium chloride, glucose, which is sugar, and caffeine, which is composed of carbon, hydrogen, nitrogen, and oxygen. So you can see that they're composed of multiple different elements. So when you combine two or more elements together, they form a compound, which is basically a completely new substance. And they're different in a lot of ways. So like, for example, if you look at hydrogen gas reacting with oxygen gas, you get a completely new substance, water, H2O. And they're different because they have very different physical and chemical properties. So for example, if you look at boiling point, their physical state, right, solid, liquid, or gas, and also their flammability, which is an example of a chemical property. So if you look at hydrogen gas and oxygen gas, for instance, their boiling points are different. So hydrogen gas boils at a much lower temperature, negative 253 degrees Celsius. Oxygen gas boils at negative 183 degrees Celsius, but then water, the new substance that's formed, boils at 100 degrees Celsius. So you can see here that the physical properties are very, very different. So when you look at the physical state, you have hydrogen gas and oxygen gas. At room temperature, they are in gas phase or gas state, whereas water at room temperature, it's liquid state. And in terms of flammability, hydrogen gas is very flammable, right? Oxygen gas, it's not flammable, but it is required to make fire. Okay, so it's required for combustion. Combustion is anything that burns, is a combustion type of reaction. Water, on the other hand, is again completely different from the other two. It extinguishes fire. And so, again, this proves that you can have multiple different elements with different physical and chemical properties, but then when you combine them, you get a completely new substance with completely new physical and chemical properties. Let's look at the difference between compounds and mixtures in terms of their chemical composition. So let's say, for example, we have this container here containing water, and you know that water has the chemical formula H2O. So when you look at the chemical formula, the H2O here, you basically have 2 parts hydrogen for every part oxygen. And according to the law of definite proportions, the law that you learned in the previous chapter, regardless of where you obtain that water from, the ratio between the 2 elements, hydrogen and oxygen, will remain the same. Okay, so that's true for any compound, not just water. It's true for sodium chloride, true for aluminum oxide, for glucose, sugar, so on and so forth. So in every compound, the elements combine in fixed definite proportions. Okay, so sodium chloride, for example, it's always 1 part sodium, 1 part chlorine. Same thing for sugar. Let's say glucose. Glucose is the chemical formula C6H12O6. So for every 6 carbons, you have 6 oxygens and 12 hydrogens. But this is different when it comes to mixtures, because in mixtures, you have several different compounds that are mixed in together in the same container. So let's say, for example, we have a mixture of hydrogen gas and oxygen gas. And you know that hydrogen gas is composed of has the chemical formula H2, and oxygen has the chemical formula O2. And so in mixtures, you can control this ratio between the 2 elements, hydrogen and oxygen. Let's say you can put 2 liters of hydrogen and then 1 liter of oxygen, and then the ratio can vary depending on how much volume you added into that container. You can have 2 parts hydrogen for every 1 part oxygen, or you can have 2 parts oxygen per 1 part of hydrogen, and so on and so forth. So in mixtures, the elements can mix in any proportions. But our focus here will be on compounds and not mixtures. So compounds are basically composed of atoms, elements, right, that are held together by what they call chemical bonds. So chemical bonds are the result from the attractions between charged particles. And we're talking about subatomic particles such as the electrons and the protons. So you have the negatively charged electrons and the positively charged protons. We don't care much about the neutrons because they are uncharged and they're not really involved in chemical reactions. So there are 2 types of chemical bonds. There's what they call ionic bond, and the other one is covalent bond. So make sure that you remember the difference between these 2 types of chemical bonds. There's actually a third one, but it's outside the scope of this lecture. So an ionic bond is basically a bond between a metal and a non-metal. And so salts, for example, are composed of a metal and non-metal, like sodium chloride. Sodium is a metal, chlorine is a non-metal. And so when they interact together, they do so via an ionic bond. So they are held together by this type of bond. By definition, an ionic bond involves the transfer of electrons from the metal to the non-metal. So remember that in the previous chapter, metals tend to lose electrons. And in that process, they turn into a cation with a positive charge. On the other hand, the non-metals tend to gain electrons. And so in the process, they gain a negative charge. And so they're called anions, right? So cations for positively charged ions, and anions for the negatively charged ions. So that's what ionic bond is. It's basically the transfer of electrons from a metal to a non-metal. So for example, this is how you would write a metal losing an electron. So you have an arrow over here. On the left hand side of the arrow is the before and then after. Okay, so this is the before and after. So before, the metal has a zero charge. So it doesn't really indicate that, but it's implied that there's a zero charge there. So that was before, and then after it turns into a positive charge. It turns to a cation because it has lost an electron as shown here. So if you have 2 electrons here, that means you have a positive 2 charge. If you have 3 electrons, you have a positive 3, and so on and so forth. And so the nonmetals, as I mentioned earlier, they tend to gain electrons. And so this nonmetal, again, this is the before and this is the after. So this nonmetal will receive that electron from that metal. They just release an electron. So this nonmetal receives the electron and in that process gains a negative charge. And so this is what they call an anion. So now we have a positive charge and a negative charge here, right? A cation and an anion interacting via electrostatic interactions, okay? Because you have a positive and negative charge. So these are, this is what they call electrostatic interaction, which is what an ionic bond is, essentially. So the compounds that utilize ionic bonds are known as ionic compounds, okay? And a lot of these ionic compounds, they contain ions that are arranged in a very specific manner, okay? They have a three-dimensional arrangement. So the one that's shown here is for sodium chloride, table salt. So you have sodium ions or alternating sodium and chloride ions. And so they form this three-dimensional arrangement, which is called a crystal lattice. Okay, so a lot of ionic compounds, they have what they call a crystal lattice, which is basically a very specific three-dimensional arrangement. And it's different for every ionic compound because they are composed of different elements. Covalent bond, on the other hand, is the bond involved in nonmetals. Okay, so it's the bond between nonmetals. So this bond, covalent bond, involves the sharing of electrons between 2 or more nonmetal atoms. So take note of the difference between covalent bond and ionic bonding. So in covalent bond, it's the sharing of electrons, whereas in ionic bond, it's the transfer of electrons. So there's a lot of examples of compounds that utilize covalent bonding. So compounds that utilize covalent bonding are known as molecular compounds. Okay, so you have a bunch of nonmetals that are bonded together via covalent bond, and you get a molecular compound. And another word for molecular compound is covalent compound, or the more well-known term would be molecule. And there's a lot of different types of molecules. You can have organic molecules, which are molecules composed of carbons, hydrogens, and nitrogens. Water is an example of a molecule. It's composed of hydrogen and oxygen. Both hydrogen and oxygen are nonmetals. And so the bonding between the hydrogen and oxygen is covalent in nature, a covalent bond. There are several different ways that you can represent compounds. There are 2 categories that we're going to cover here. The first one is chemical formula, and the second one is called molecular models. Chemical formula basically indicates the elements present in the compound and their relative number of atoms or ions. And so let's say, for example, water. Water can be represented by its chemical formula H2O. And this tells you that you have 2 atoms of hydrogen for every 1 atom of oxygen. Sodium chloride has this chemical formula, NaCl. So you have 1 sodium per 1 chlorine. And carbon dioxide, 1 carbon for every 2 atoms of oxygen. You could have glucose, which is again C6H12O6. And there are actually 3 different types of chemical formulas. We have empirical formula, molecular formula, and structural formula. By definition, empirical formula is the formula that gives the relative number of atoms of each element in a given compound. In other words, it's the simplest whole number ratio between the elements. So before I give you an example, let's look at the definition of the other two first. So the second one here is called molecular formula, and this gives the actual number of atoms of each element in the molecule of a given compound. And finally, structural formula uses lines to represent the bonds and shows how atoms are actually connected or bonded to each other. So let's look at an example. Let's say we have hydrogen peroxide, and the chemical formula or the molecular formula of hydrogen peroxide is H2O2. So you have 2 atoms of hydrogen for every 2 atoms of oxygen. What would be the empirical formula of this compound? Well, if you look at the definition of empirical formula, it's basically the simplest whole number ratio between the 2 elements. In other words, it's the simplified version of the molecular formula. So how do you simplify this formula? Well, you have to look at the subscript, right? It tells you that you have basically 1-to-1 ratio between the hydrogen and oxygen. For every 2 hydrogen, you have 2 oxygens. And so you can simplify this further into H1O1 or simply HO. So HO is the empirical formula for the compound hydrogen peroxide with a chemical or with a molecular formula H2O2. So that's the main difference between molecular formula and empirical formula. Empirical is the simplified version of the molecular formula. Structural formula basically shows you the bonds, right? And it's represented by lines. So here you have hydrogen, and it tells you that hydrogen is connected to the first oxygen, and then the first oxygen is connected to the second oxygen, and then the second oxygen is connected to the second hydrogen. And we're going to talk about structural formula in greater detail in later chapters, like chapter 9 and 10. Another way to represent compounds is via molecular models. And molecular models are actually more accurate and complete way to specify or represent a compound. And there are 2 different types. There's the ball and stick molecular model, and there's also the space-filling molecular model. In the ball and stick model, you have the atoms are represented by balls and chemical bonds are represented by sticks, hence the ball and stick molecular model. And a lot of these atoms are color-coded. Okay, so hydrogen is typically given the white color, carbon black, nitrogen blue, all the way to chlorine green. So an example of a compound here represented by a molecular model via ball and stick model is chloroform. Okay, so the chemical formula of chloroform is CHCl3. This model of chloroform shows you how the atoms are connected to each other, right? So it tells you that the 3 chlorines and the hydrogen are all connected to the carbon, and the carbon is the central atom in this case. And so in a lot of molecular models, it shows you the shape of the molecule, and you'll learn about the different shapes of molecules in chapters 9 and 10 towards the end of the semester. The second type of molecular model is called the space-filling molecular model, and this is similar to the ball and stick, except the atoms fill the space between each other to more closely represent how a molecule would actually look like if scaled to visible size. Okay, so this is what a chloroform would look like via the space-filling model. And so now the bonds are actually omitted here, right? The lines, I should say. The lines are omitted. And it shows you that the atoms actually overlap a little bit. And that's the more accurate way to represent molecules. So before we shift completely and permanently to compounds, let's talk a little bit more about elements. because there's actually two categories of elements. There's what they call atomic elements and molecular elements. Atomic elements are those that exist in nature with single atoms as their basic units. So what that means is that these atomic elements are the elements that can exist in stable form as single atoms, okay, containing single atoms. And a lot of these atoms are actually metallic, okay. These are the metals as well as the noble gases, because as you learned in the previous chapter, the noble gases are very stable elements, right? They're the least reactive. They are the most stable elements in the periodic table. So most elements fall into this category, and some examples are aluminum, right? You can have a single atom of aluminum that can exist. You can have sodium, neon, magnesium, gold, silver, and again, the noble gases. Molecular elements, on the other hand, don't normally exist in nature with single atoms. So what that means is they typically form bonds with other similar atoms. So for example, they can exist as molecules containing two or more atoms of that same element. So the homonuclear diatomics that we talked about earlier, those are examples of molecular elements because they contain a minimum of two atoms of the same element that are bonded together. So hydrogen gas, nitrogen gas, oxygen gas, fluorine, chlorine, so on and so forth. They all contain multiple atoms of the same element. You can also have polyatomic elements that fall in this category, like P4 and S8. So just like the elements, the compounds also fall in two categories. There's the molecular compounds and ionic compounds. So I mentioned earlier that the molecular compounds are those compounds that utilize covalent bonding, right? Covalent bonds. So they're composed of two or more covalently bonded nonmetal elements. So again, H2O is a perfect example. So the basic units of molecular compounds are the molecules. So you have molecules in molecular compounds. Again, so if you have nonmetals that are bonded together via covalent bond, then you have a molecule. Again, water molecule, carbon dioxide, methane, alcohols, those are all good examples of molecules. Ionic compounds, on the other hand, are compounds that utilize ionic bonds. And so you have basically a bunch of metal and nonmetals that are interacting together to form an ionic bond, right? So it's an electrostatic type of interaction. The basic units of ionic compounds are known as the formula units. So you can have sodium chloride. The formula unit for sodium chloride is NaCl. So again, if you have a cation and an anion interacting with each other, then you have an ionic compound. Here are a few examples. You have NaCl, which is sodium chloride, KBr, which is potassium bromide, calcium carbonate, and so on and so forth. Okay, so let's look at some examples here and see if you can really identify and differentiate atomic element from molecular element, molecular compound from ionic compound. So again, you can pause this video if you want to give this a shot. So the first one here is xenon. And we know in the periodic table that xenon is one of those noble gases. And we know that noble gases are stable, and so they can exist monoatomically, meaning one atom, single atom. So this is a perfect example of an atomic element. So xenon is atomic element. What about nickel 2 chloride? So NiCl2, as you can see, when you analyze the chemical formula of this compound, you have nickel, Ni, which is a metal. And chlorine, when you look at the periodic table, chlorine is a nonmetal. So a metal plus a nonmetal gives you an ionic compound. And the third one here is Br2. So again, when you analyze this, you have two atoms of the same element, bromine, which makes this a molecular element. The fourth one is NO2, nitrogen dioxide. As you can see, nitrogen is a nonmetal. Oxygen is also a nonmetal, and so the bonding between them is covalent in nature. And so nonmetal plus a nonmetal gives you a molecule. So this is a covalent or molecular compound. And the last one here we have NaNO3 or sodium nitrate. So you have sodium, which is a type of metal, and you have a nitrate, which is a polyatomic ion that's composed of nonmetals. So you have nitrogen and oxygen, both are nonmetals. So in other words, you have a metal plus nonmetals, which makes this compound a ionic compound.